Okay. Good morning, everyone. So before we go any further, let's revisit where we left off on Tuesday. And we did have some questions about, as we were leaving, row major versus column major, and maybe it's worth taking a step back and talking about memory layout in general. So just as a quick show of hands, how many people here have already taken 311? Okay, so half-ish. Okay, so if you haven't spent much time thinking about what your program actually looks like in memory, it is kind of occasionally worthwhile to think about this. So real program structures are usually more than one-dimensional, right? Your memory, however, is one-dimensional. That's all you got. Memory is just one big array of bytes. And so you want a graph, you want the social network graph, billions of nodes, diameter 6, it's still going to be smashed into some one-dimensional projection, right? So everything is laid out in some sort of one-dimensional setup. And so some of these structures are going to be easy to understand how they're actually laid out in memory, right? If I have a one-dimensional array on my one-dimensional memory, unless I'm completely bizarre, I'm going to lay it out aligned, right? Where incrementing along my array, increments along my memory addresses. If I have a two-dimensional array, I have a choice, right? Which dimension matches the natural spatial locality of my physical memory space, right? So a lot of languages, this is a language level decision, right? Assume that row major is how you're going to lay these out, i.e. if you have a set of rows and columns of your matrix, then sequential movement within a row is sequential movement in your one-dimensional address space, and movement along a column is probably some very large jump, right? They're very far apart. So A of 1 comma whatever and A of 2 comma whatever may be thousands, or again depends on the size of your structure, thousands or hundreds of thousands, how many bytes apart, right? So actually a whole lot of interesting things that happen if you're looking at column formats. How many people have ever taken, well, you took the class or not, might not matter. How many people have investigated the ways that databases optimize layout? Nobody? Okay, well, so obviously rows and columns are kind of important in databases as well. Their memory layouts actually have to be a little more complicated because they're actually worried about how it's all going to look, even not just in memory, but on disk. So these sorts of data layout questions are pervasive across computer science, right? But for the purposes of what we're looking at with respect to caching, we're just going to worry about the alignments between the virtual space, the physical space, and how things are laid out. Similarly, if you have structs, objects, right, they have their own internal memory layout. Again, language specific. Sometimes it's fully entailed exactly how that's going to work out, right? So if you look at the C standard, it tells you how a struct is actually going to be laid out in memory to some great degree. If you look at some other language standards, exactly how does Python lay out its objects as bytes in memory, yeah, good luck with that. Okay, so if we assume that we want to actually understand the locality of what we're accessing, then the order in which we access these different structures either can align better or worse with the way our cache system actually works. Because our cache system, in its fundamental unit that we're operating on, much like our main memory, is also one-dimensional, right? It's a cache block. So even if your processor has a completely scalar interface, load word, load byte, right? I want one element, right? Caches don't care about elements, they care about blocks, and blocks are just short little vectors. Right? So you'd really like your short little vectors to line up with the way that you're accessing your structure if you want to actually exploit locality well. Right? You can go deeper down this rabbit hole with n-dimensional nested loops and multi-level hierarchies of sub-blocking that are algorithmic changes to try to maximize the way that local work elements can fit in particular level of cache. But this level, at least, hopefully should be pretty natural, right? So if I change for, in terms of what work I'm doing, for J for I, do something on A of Ji, or I for J, do something on A of Ji, right? Assuming that the logic in that inner, in the actual body of that loop is, pretty straightforward. Like, let's say I'm just summing them all up. I'm doing the same work, right? There's no deep fundamental change in the work that I'm doing, but the order that I'm doing it in could have enormous changes on your performance, right? So again, imagine this matrix is really, really big. Imagine N is very large. Imagine the fact that N is so large that consecutive elements in J, i.e. in the column space, are more than 4K apart. Great, now you've entangled the virtual memory system in here because they're not even on the same page from access to access to access to access, right? Then you get into really fun problems like the fact that your TLB may only have like 64 entries. So now you can even only remember where the last 64 columns were, and if you got 64 rows were, you got thousands of rows, well, you're a bit host. So you'd much prefer this version, right, where these, as I increment I, right, these are consecutive in my memory space. Okay. All right. So spatial. Okay, now, here's another fun one. How many people are familiar with the computational complexity bounds on quicksort versus radix sort? How many people are familiar with the computational complexity bounds on quicksort? Okay, that's a little terrifying. When I say computational complexity bounds, if I ask you big O notation, what's quicksort big O of? Yeah, I didn't ask average. I asked what's the big O. So it's big O of, actually big O of n squared. Average case is n log n, but worst case is, right? But yes, as mentioned, average, it's a probabilistic algorithm. If you do it right, right? How about radix sort? How many people are familiar with what radix sort even is? Radix sort, also known as bucket sort. Apparently we don't teach sorting anymore. I guess we just all rely on the sorting hat or something. I don't know. Okay, so radix sort, let's say that I'm sorting a deck of cards, right? There are only 52 possible distinct values. I just get 52 buckets. And when I see a card, I throw it in the right bucket. Right? So there's a little more complexity to it. It's not actually O of n. There's some other terms in here related to basically the size of the range, how long it actually takes you to figure out where to put something, right? But these are factors that are not proportional to the number of elements. They're proportional to the representation of an element, right? So there's some other things in here, but this is, if you look at a purely theoretical bound, it's better than n log n, right? It should be roughly linear. And yet, if you look at all of these examples, right? So here's radix sort, here's quicksort. Let's assume that these are not pathological and you really are getting something that looks n log n, right? The number of instructions per item, where k is the number of items to sort, right? Radix sort is going to win. You will execute fewer instructions doing radix sort. The theorists were not lying to you. There are, right, fewer operations required to do the radix sort. How does time look? Radix sort doesn't win. Why not? Right? Things are getting better, and then not so much. The answer is caching, right? Radix sort has no particular locality, right? I throw this over here, I throw this over there, I throw this over here, I throw this over there. Yes, there's some hierarchy to it. You have a set of iterative passes. You can do this like bitwise, right? While you're moving a bunch of data around, there's no locality. Quicksort gets very local very quickly, right? Every time, every pass that I'm doing, I have better and better spatial locality, and I have enormous amounts of temporal locality as I recurse down. And operating the same data items over and over and over again with high probability. And you can see that in the cache miss rate. So what you can take away from all this, finite resources, right? The types of optimizations we're actually employing in real systems have very important impacts on whether or not things like asymptotic complexity are ever realized in the way that you might think they would be. Right? Even though in theory, radix sort, right? Better. Except in very particular cases, you probably still just want to use quicksort. Right? Because it actually uses the resources you have well. Right? There's also the similar reasons why when you look at matrix multiplication, right, you get naive matrix multiplication n cubed, right? Pretty straightforward, right? For every row, for every column. Right? Strassman's algorithm gets it down to around n to the 2.7 something. With some recursive subdivision, some trading and multiplication NADs. And then there's been a bunch of work further to get that 2.7 closer and closer to like 2.5, but almost no one uses anything further down the chain than Strassman's, because the rest of the constants get large, right? And they aren't actually friendly with the way that we actually build the machines. Right? So, in particular, if you think back to your AMAT, just the more light, there we go. When you think back to your AMAT, where that last chunk of it, right, might be in like 240 cycles, right? It's pretty reasonable. 60 nanoseconds at 4 gigahertz. Anything you can do to avoid this is huge, right? Anything you can do to spend more of your time further to the left in your AMAT equation gets you a lot of value. Right, something that fits in cache or not, right, can be 10x. Something that fits in main memory could be hundreds of x. Right, so asymptotic, it doesn't matter if your constants exceed your own lifetime. Right, so another example, real life that I ran into, there was a string matching algorithm, and the state of the art, right, was linear. You know, some additional fun stuff there, but effectively linear. But because of the size of the items that were being worked on, it was linear in the speed of disk. And if you swap that out for an n log n algorithm that ran at main memory speed, you turned weeks into hours, right? So pay attention to your memory system. Bloop. Okay. So let's think about what's going on in your cache a little bit here. Cache can be idle. You can get a request. You can actually do the work to check if something is ready. You return it. If not, you can do a miss. So we can even stop you right here. Okay. This part is the one that you want to primarily optimize for latency. Right. I want to be able to make sure I can get back to my requester if I can actually serve it as fast as humanly possible, right? Everything after this, all the rest of this, we'll keep going. This is failure. We've already failed, right? How long we take to fail, right? We can play games, right? So if I want to figure out where to put something new, right? Once I've already figured out that I can't serve the request, I can afford to have more complicated policies here, right? So you can talk about the sort of front path and then the back path on your cache, right? You always want to optimize your cache for the case where it's actually serving the requests that are coming to it well, right? But here, if I want to do something fancy, yeah, I got time. Right, again, if I'm already missing, right, nothing's going to happen for a bunch of cycles. I don't need a one cycle answer to most of this. I can buffer this stuff up and deal with it once it comes back. If I'm missing to even my L2, right, that's going to be, another 10 cycles. So if I need 3 or 4 cycles to do a little more math or do a few more comparisons, it's worth it. I get a better choice on what I'm doing here. Right. Right. We'll walk through the rest of the state machine. I'm not going to worry about it too much. I really just wanted to highlight the fact that your goals in different parts of this can be subdivided further. You don't need to do it all in one quick fell swoop. In particular, one of the things that you can start looking at, and it's not really worth bothering when you're talking about a small cache and only in one level. I'll get to that just in a second. Let me go do a little more chalk work. Think about your data and your metadata in your cache. Think about where that cache controller has to live. If I've got a small cache, then again, my cache is ultimately built out of SRAM, right? Then probably my tags and any other, valid, dirty, etc. metadata bits here are probably all literally on the same line, physical wire, right? That I'm going to light up and then send all these bits down to whatever needs to read them. If it's more associative, there are going to be multiple copies of these across. But if it's small, for physical implementation reasons, I'm going to literally put everything that I want to light up on one physical wire. Right? That's the simplest way to do it. I access this set. Everything on the set is on this wire. I read it out. Great. Now imagine I have an 8 megabyte cache. Do I build it the same way? No. I do not want to run a wire through multiple, millimeters of my chip, driving an enormous, set of buffers across. No, it's not how I'm not going to structure this at all. In particular, at some point, I'm going to take advantage of the fact that this data here is substantially smaller, right? The metadata is substantially smaller than the data that it is covering, right? So do some back of the envelope. If I've got a 64-byte cache line, and let's say that I need on the order of, 40 bits a tag. Let's assume that for whatever reason, I have a whole lot of replacement policy and additional metadata. This whole thing is going to certainly be less than 64 bits, right? So I should have an at least 8-to-1 ratio. We'll practice a bit more, right? More like 10-to-1 between my data and my metadata. Now, again, remember that physics hates us. The speed of signal propagation is finite. Now, I have a request coming in on some wire, right? Got some cache controller, right? That's going to sort of start processing this request. I can put my metadata here. I can consolidate it from across the entire cache. It's maybe 10% of my total cache or less, right? So then the entire cache is now like this. Wherever this physically comes in, I can be doing my lookup here. I can get this response faster, even if I launch these at the same time, than walking, the H tree to actually finally get to some particular cache line of 64 bytes that I'm then going to send back. Right, so again, you can play games with your front side, your back side, right? What you're trying to do, how quickly you're trying to get a response. So even here, right, when we talk about our AMAT equation, there's a gross simplification and access time, right? Because I could actually figure out whether or not I get hit or miss for a large cache actually quite a bit faster than I could actually get the data back. So actually determining hit and miss and then launching a miss, right, is something I could actually have that is less than the access time of this cache to actually return the data, right? Are we going to actually worry about that in terms of asking you to AMAT questions? No, but I want you to understand what you're approximating in your models. I want you to understand how spherical a cow we are assuming in order to make the equation simple. All right, so the things that you do when they're small, very natural, physically aligned. Again, the physical implementation, the finiteness of resources has important details. I'm going to consolidate my metadata. This is a faster access than getting the data, the games to be played. This is going to be even more important when we get to multiprocessors, where we are going to get requests for data that we actually hope we don't have, because then we don't have to do any bookkeeping. These are requests from external entities. So you're actually going to start thinking about from your cache controller, again, even more so, I want to be able to very quickly tell you yes or no that the data is present, even if no one is actually requesting that data, and I need to go do updates to its metadata. Right, so more to come on that when we go to multiprocessor. Again, even this actually will turn out to be a gross oversimplification, because real caches, if you look at a die photo, you'll note that you've got all these chunks of your large level caches. So your large level caches are heavily banked. They may in fact have a network connecting the different portions of them, right? So they're not actually built in a monolithic fashion. As you start to scale things up, they get more complex. Just FYI. Yeah, we'll come back to this. Okay. So there's some games you can play your controller. Optimize for actually getting the response back if you can. Optimize for at least figuring out when you need to hit or miss as fast as possible. Great, let's move on. The next sort of basic thing that you obviously want to do with your caches is to try to give reads priority over writes, right? This is a standard issue throughout the entirety of your design, that loads and stores are fundamentally asymmetric, in that the loads need the data, the stores already had the data, right? So you can sort of propagate that same thought through the rest of your system as well, right? So if I have conflicts among pieces of data, if I have different policy decisions to make, any time that I have a choice, I am always going to want to make, loads have preference over stores. What does this entail, right? What am I going to have to spend to be able to do this? It's almost always going to be some more buffering, right? So I can buffer more stores, right? Is there a downside to making the buffer bigger, right? What's my back pressure on sort of indefinitely delaying, right, processing all of these stores? Again, do a simple thought experiment, take it to its illogical extreme. Imagine I buffer all the stores. Congratulations, your write buffer is now bigger than memory, right? So obviously at some point, it's not a write buffer anymore. It's become larger than the memory system it's serving. Clearly, the write buffer can't be too large, or you can't check it in parallel with on the way to the next memory and so forth. But again, the right thing you take away from this is not what specific choice to do, but think about every time that I have a choice, prioritize the reads over the writes. Okay. Okay, so this should get us through the basics. I was actually hoping to get by the end of Tuesday, but that's fine. So cache size, block size, associativity. These are all things that we covered quite a bit back in 331. There's an enormous space of replacement policies. This gets even more interesting if you start looking at multiple different technologies in your cache. There's actually been a lot of work over the last decade plus on hybrid volatile, non-volatile memory caches. Right, so starting really with PCM work in the 2009 or so. Micron even actually sold PCM memory for a while. MRAM still an interesting topic for a lot of people to look at. So there you have all sorts of interesting replacement policy questions. All right, the replacement policy obviously interacts with things like inclusivity choices in a multi-level cache hierarchy, right? And optimal choice everywhere on every level of your cache is a compromise, which is why having multiple levels is going to be good for you. If you want to reduce the hit time for a particular level of your cache, make it smaller, make it more direct map, that's going to increase the miss rate. So there are games to play with your L1 versus your L2 if the sizing in your workload matters. Otherwise, you still even on your L1, as we saw with those Intel numbers, reasonably high associativity. Right. Bigger caches, we'll come to victim caches in a second. More levels of the cache, right? Every level beyond your L1 is ultimately really sort of optimizing this feature. Your L1 is fundamentally co-designed with your processor pipeline. Can't be otherwise. Right? I need to be able to serve my accesses to memory at the rate that they're coming in. Right? I need to make my common case hit behavior, have the whole thing function without breaking my CPI. The rest of this are often physically decoupled. They're not even at the same clock rate. On the other side of some bus, right? Lots of cache levels, up to the point where AMAT tells you should stop, right? Where the hit rate that you're getting versus the time to go check another cache would have been faster to just go ahead and access the next level. Okay, so what are some things that you can do that go a little further? Right, so what if I want to reduce my hit time? Right. So I want to have a good miss rate, but so I'm going to invest in some associativity, but I can do, say, weight prediction. Are there things that I could do to learn from my past history to make particular patterns easier to serve? Trace caches, right? How do I increase the effective bandwidth of my cache? What are the ways that I can organize the internals of my memory system? What are the limitations? What are the cost trade-offs there? Okay. We'll go over the rest of these as well. Okay, so again, physics, smaller is faster. So simpler is faster. So if you look at the impact of associativity, right, for small caches, right, for small caches, the relative change in associativity is a large chunk of the total time, right? There's a real cost there. By the time you get up to a large cache, the associativity isn't what's killing you. It's just literally getting to different parts of the cache, right? So how much you care about making this part small and fast is a function of how large you are. But even if you're looking here, right? Modern, low-level, close to processor caches, 64 KB, 128 KB. Yes, I know we're not in 32 nanometer anymore, but it's what it is. You can see that this impact is still very visible at this point, right? So you can still get some mileage out of trying to make a cache that has the miss rate of a higher associative cache, have a hit time that looks more like, in the common case, a less associative cache. There's still mileage to be gained there. Okay. So how might you do that, right? Because you probably don't want that miss rate. I mean, you could just get faster hit time, but yeah, probably not worth it. So how might you do it? Well, you can use weight prediction. So I don't actually have to check all of my ways in parallel, right? The data could be in any of them. I have to make sure before I decide that I actually have a miss that I have checked all of them, but I can guess as to which of the different places it could be that it is. And if I'm right, then I have the hit time properties of a direct map cache. Almost. I mean, there's some extra muxing overhead that's still there. I have to actually really get to all the ways. Right? Have to be paths physically. There are costs. So in particular, right, let's ponder the following. I've got some piece of data and it's got very good temporal locality, right? My variable I keep touching my variable I. Fine. Well, if I is still in cache, hasn't left the cache, it will still be wherever it last was in cache. right? So if I look at the instruction, we've got a load and a store pair. Again, why it hasn't been promoted to a register for an I++, let's not ponder such things. Maybe our compiler writer fell asleep at the wheel. Maybe whoever did the build script, pushed everything to -0. Let's just say I've got some I++ happening over and over again, right? Got a load, I got a store. I can associate those load and store PCs with the particular way that that data happens to be in, right? And that prediction will have pretty good accuracy, right? If I have I equals 0 to 1,000,000, and I keep loading and storing to I, again, yes, it'd be in a register, but spherical cows. And then wherever it happens to be the first time, I'm going to guess and have no idea. I'm going to probably be wrong, right? But then I can update a predictor associated index by PC that says, oh, I think you're in way 3, right? And once that mapping is correct, modulo aliasing and forgetting in the predictor itself, as long as I stays in cache and doesn't get evicted, I is not going to move, right? We allocate it to some particular way. It's going to stay there until it gets kicked out of the cache, right? So your prediction rates can actually be fairly reasonably high. Not branch predictor high, right? We're not looking at high 90s, but you could easily get 70-something% accuracy here, right? Now, what do you do if you miss? Or what do you do if you're wrong? Well, if you don't have a hit, you do have to go check the rest of the ways, right? You can do it serially, check them one at a time. Again, depends on how you built the hardware, right? You could go check them all in parallel, but again, if you're doing this properly, this is on the less common path. Right? You can even think about how this would actually play out in terms of AMAT. Right? You could even sort of think about your initial access has some percentage of the time to actually be a correct access, and then the rest of the percentage of the time has the full cost of going through the rest of your L1, and then some of them actually are actual misses. It's almost like you've sort of had 2 levels of caching within your single cache. Right? So let's say at a 4-way. Cache, I need 2 bits to figure out where I'm going. Not a whole lot of metadata to keep track of. Right, this way predictor doesn't have to be particularly large, right? And then I can go and index it accordingly. Right, and in particular, in this design, right, you're set up. You could actually have a structure that, in terms of what you're accessing, looks a bit more like a direct map structure where you have to find the relevant way bits in order to index into a larger structure. Again, makes a lot of sense for a small cache to build it this way. If you're looking at very, very large caches, they also use way predictors, but they use it for a different reason. So if I have an enormous distributed L3, why might I be interested in way prediction other than hit time? Right, so go back to our that slide where we compare doing floating point multiply accumulate 20 picojoules versus sending that data down a wire 25, 50 up to nanojoules. Right. So in a very, very large cache, my goal may not be the performance. It may be how many accesses do I send out speculatively, right, before I've bothered to finish the lookup of exactly where something is. I think, again, think about this model here. If I actually have a highly associative cache and I wanted to do all the lookups in parallel, I might be basically requesting a large amount of work in the sense of joules equals work, right? Instead, I might start my lookup here, speculatively send one of the requests to get the data started, right, on the hope that it is a hit and I picked the right way, but I'm not going to invest in, say, doing 16 of them at once. It's just not a good energy investment. Right, so there are other ways that you might have way prediction. This shows up again when you look at Nuka caches in particular. Okay, so fast, low power, potentially slow when it misses. Okay. trace caches, right? So if you've done something once, you might do it again, right? So you can build dynamic traces of, traditionally trace caches have been deployed for the instruction caches. So if you say trace cache, people are going to assume you're talking about instruction cache. There are similar things that happen for the data side. So the word that I was looking for on Tuesday for the style of prefetcher that is like, that is basically the corresponding version of this, is called a neighborhood prefetcher. Right, so you have a pattern of temporally correlated deltas that you call the neighborhood. But let's talk about instruction caches, right? So in an instruction cache, one of the challenges that we saw with going very wide, right? So again, think about your 2022 scale AMD with your 10 wide potential integer issue, and recall that the average length of a basic block is like 5 instructions, right? And it's x86, so those are actually actually pretty tightly packed. And so the challenge you're going to come into there is I'd like to not be dealing with all that nasty misalignment, low fetch utilization, which I'm going to get in sort of walking some path through my control flow graph that is not contiguous in my memory space, right? So if I've got some hot path through my code, right, but it's got some branches in it, it's got some jumps, right? They're not going to all be lined up nicely from byte 0 to whatever. They're going to be wherever the particular pieces of those code are that you happen to be walking through that graph repeatedly. Right? At the very least, I have to skip over the parts I didn't take in every if else. Right? It's going to be at least slightly sparse. But the particular code that I'm executing might be the same path over and over and over and over and over again. Right? So I could record it. I could get a trace, a dynamic trace of the executed instructions, and I could cache that rather than just the instruction bytes directly. Now, I need to make sure that I'm on the right path. So there's a bunch of additional logic to make sure that the branch predictions that are inherent, right, actually still hold. Right? I do actually have to go still execute these branches in there, but I can strip them out in practice and effectively compact and linearize a set of executed instructions. So this first time we saw this in Intel processor was the Pentium 4. And now again, with Intel processors, if you recall, they translate from x86 into microcode. So they're already doing some dynamic caching of a different version of the binary in the first place. This is just going a little further. Right. Right. Now, the address mapping is fun. Right. So again, you want to now try to think about aligning your runs with your cache system, trying to feed everything. If you do have paths which are different paths that keep getting taken, you can get redundancy. Right. So let's say that there are 2 different paths that I take most of the time out of the 4,000 paths I might be taking, but those 2 different paths actually share 30% of their code. Well, okay, I've duplicated that. Do my mutual compaction. So trace caches are not terribly efficient in terms of utilization, right? These are pure performance. I'm spending area to get performance. And again, if my predictor isn't good, my trace cache is useless.